So we left off last time with a review of exponent laws and an introduction to what a logarithm is. Now we're going to get into the applications of logarithms and also how you would use your calculator to do calculations with logarithms. So we're going to go from example 70 until the end of the booklet. So I think that's 32 questions in total. You'll find that most of the questions are quick. So there's a lot of mechanical and repetition, and it's really just the last few examples where we actually do some word problems. So anyway, let's get going on this. So turn to example 70, and we'll get started. So when we were talking last time about logarithms, you had a base, and the base could be anything. But now, when we're talking about using the calculator, most of your calculators don't have a special button on there that can do any base. So you need to be aware of two key buttons on your calculator. The first one is called the common logarithm. So it says here, what is a common logarithm? A common logarithm is simply a logarithm in base 10. So that's it, okay? A common logarithm is a logarithm in base 10. So when you write something like log base 10 of whatever, you could also just say log of whatever. It's the same thing, okay? So if you don't see the 10 there, it means it's base 10. If you've taken any science in high school, or if you did compound interest at some point with logarithms, then you would definitely have seen this before. So finding the common logarithm of a number, you have a calculator at your disposal now, and you can just type it. So for example here, if you wanted to find the common logarithm of 1,000, you would just type log of 1,000. But what's log of 1,000 on your calculator? Correct. Now remember that there's a statement that is a companion to this, the exponential form. So this is really saying 10 to the 3 is 1,000. Let's repeat that again for the next one. So log of 500. Let's go with 2 decimal places. What do you get for log of 500? Thank you, Graham. And there's a companion there which is saying that in exponential form, 10 to the 2.70 is approximately 500. We're just kind of playing around with using the calculator really for the first little bit today. One more answer here, and then I'm going to discuss a pattern that you might be observing right now. What's the logarithm? So when I say the logarithm, I'm saying the common logarithm. And that's what you should ultimately infer. What is the logarithm of 100? Or what is log of 100? Thank you, Jaden. So on the side here, in exponential form, that's 10 to the 2 equals 100. Notice that sometimes the number is really nice, and other times the number is weird. Like 2.70 is not something that you could guess exactly, at least not easily. However, you could find the logarithm of 1,000 and 100 very fast because they're both powers of 10. So at least though, for this one here, you should be able to understand that the answer has to be between 2 and 3, because when you go for 1,000, it's 3, and when you go for 100, it's 2, and since 500 is somewhere in between, then the answer is going to be somewhere in between 2 and 3. You don't. It's not a proportional relationship. It's not like halfway or something, or 50% or 40% or whatever of the way between the 100 and 1,000. As far as you're concerned, it's just in between. So the guess I would usually in my head just say, oh, it's 2 point something. At least I know in advance before I go and type it on a calculator, and then because the calculator, you don't want to just say, oh, the calculator tells me everything. So we don't want to be that oblivious. So anyway, the next question here is just another common logarithm. This one here is something you could do in your head because it's a power of 10. 0.01 is 10 to the negative 2. But even if you don't see that, you can still do the question. You just have to, unfortunately, use the calculator. Nothing wrong with that. It's just you're slowing yourself down. See, let's say that you were really familiar with the idea of getting it in your head, like a mental math, then you could cut out a lot of time. You don't have to pick up your calculator every time to do a silly calculation. So let's go to another example here. And this is one now where we actually are going to use a rule that is not obvious. So I'm going to familiarize you with the rule here that allows you to get the logarithm of any base if you don't have the special button on your calculator. So on your calculator, you can use the following property. So I'm just going to copy it out for my notes here. This is in the booklet. It's on page 4 or 3. Page 3, I think, actually. This rule here. This is the rule that allows you to get the log of any base. So I'm manipulating 2 files in the background. So if you're wondering why I'm going slow here, I've got 3 files on the go at the same time. So I appreciate your patience. Anyway, over here, this is a rule that says that you can change to an alternative base like base A. And what I'm saying is, this time we're going to use base A, and we're going to let A equal 10. So if you let A equal 10, then you can do this question fairly well on the calculator. So log base 2 of 1024 would equal log of 1024 divided by log 2. All right, go ahead and type that on your calculator and tell me what you get. What do you get for that question? Yes, that is correct, Graham. 10. Okay, so that means that 2 to the 10 is 1024. Another question that you could have answered in your head, but maybe you didn't see it, and that's okay. So let's play that game a little bit more here. So log base 3 of 1 over 81 would equal a fraction, and be log base 10, so just log of 1 over 81 over log of 3. And that would equal what? What would that equal? Thank you, Siobhan. There you go. -4. And of course it is, because 3 to the -4 is equal to 1 over 81. So that is good. This type of question here, we can use the rules of logarithms. So there's a rule here that I'll just remind you about. If you have log of a to the k, it doesn't matter what the base is. That's k log a. That's a rule from last week. Let's see if we can apply it to this question. So log of 10 to the 1000. The first thing that I would do is take the quantity in the bracket, and see this 1000 here? I would do the same thing that I did with k over there. So I'd bring it in front. And now you can continue with the question. Log of 10 is something you could type on your calculator, or if you know that 10 to the 1 equals 10. So the final answer is 3. Let me highlight some stuff here. So this rule here that I used took this 1,000 and brought it here. So I'll just circle the value k there, or just kind of arrow it or something. Let's use the highlighter. So that's what I did with that, okay? And then log of 10, having issues with the highlighter here. Log of 10 would equal 1. See, log of 10 equals 1. So that's part 1 of 4 of the mechanical features of the calculator that you need to know how to use. So now we're going to talk about the common anti-logarithm. So the common anti-logarithm is the opposite or the inverse of log base 10. So anti-logarithm is an exponential, and common means base 10. Let's write that down, okay? So common, base 10. Anti-logarithm means exponential. Just some terminology, because we're not limited to just base 10. We can use other bases as well. So in other words, here the anti-logarithm would be the exponential with base 10. So this would be 10 to the 0.928. Can someone give me a number on that? Yes, that's correct. Thank you. So we can repeat this process again several times in finding the common anti-logarithm or the exponential for the following numbers. So let's do that here. So that would be how much? Yes, very good. I'm going to go to 3 significant digits and put 339. And the next one, yes, I like those answers. I'm going to go with 3 significant digits. So just an extra little bit there at the end. And that's pretty much it for the common anti-logarithm. So you just do 10 to the power. So if it was a different base, you would do whatever the base is as an exponential. This next question is your first kind of solving an equation for today. Here we're trying to solve an equation for E, where E represents energy. We mentioned this briefly last time in one of the key examples, and it was all about remembering that whenever you have an equation with exponentials or logarithms, you can write it in 2 different ways. So that's what I want to show you, equation in 2 different ways. We could have log E is equal to negative 18.49, or you could have exponential form, which is the E is the answer, the base is 10, and the exponent is whatever the logarithm equaled, which is in this case negative 18.49. And then I'd ask you, which of these 2 versions of the same equation, which of these equations here would give you the better path to the answer? So which one should we use, the left one or the right one? Yeah, definitely. You want to use the right one. And for reasons that are pretty clear, you have the answer is isolated. So you need to figure out how to type that on your calculator, but that's what I was training you with in the previous examples. So in this case, the answer for E is going to be very small, times 10 to the negative 19, and the answer is in joules. So I'm going to just ask briefly here, if anybody has, try to calculate this on your calculator, and if you have any issues, just let me know in the chat. So if anybody has tough time typing this one on their calculator, please let me know in the chat. I can wait for a minute, that's fine. How is everybody doing with the pace? Are you okay with the pace of today's class? Am I going too slow, too fast? Anybody else? Thank you. Thank you, Kyle. Thank you, Amir. Thank you, Jaden. Okay, so anyway, that's enough of base 10 for a little bit. If you go on your calculator, there's actually another button that is a logarithm button. And I mean, some of you have a button that you can do any base. I think if you have that button, then you're already familiar with the button. You probably used it in the last class. No, Joshua, the value J there represents joules. It says calculate the energy in joules. I'll put joules here. No, thanks for pointing that out. So we're going to look at another button on your calculator, which is called the natural logarithm. So natural logarithm is when you have a logarithm that's written in a different base. It's base E. Now, what is E? Well, to answer that question, I'll ask you, what is pi? Pi is a special number in math. You know, it's 3.14159, and it goes on forever without a pattern. And it's very valuable to us in many branches of mathematics. Of course, the first times you probably see it is in geometry, and then you see it in trigonometry later, and then it's actually in a lot of branches of mathematics. But another very special number in math is E. And I mentioned it briefly last time as I got you to explore doing calculations with the number E. So this is just from the page 3 of our notes here. It's just an example of what E would look like up to, I could count it out here, 9, 18, 27, 30 spots. This is E up to 30 decimal places. It goes on forever, as you can see, and it's no pattern involved. The reason I put so many decimals is because when you look at the first several digits of E, you're like, oh, 7182 So you start seeing 8s, 1s, and 2s, and you're like, oh, it's a pattern. Okay, we're good. No, it's not a pattern. That's how it starts off, and then eventually it goes off into its own little space. So we call that an irrational number, meaning that it's not going to have a decimal pattern, and therefore cannot be expressed as a fraction. So on your calculator, there's a special button for it, and the button is called ln. So you see here it says it's written simply as ln. So when you see ln, it means that it's base E. So I'm just going for my notes here to find my numerical solutions as a comparison. So just remember here, when you see ln, ln is the same as log base E. So it's understood that there's a base E there. But we're not going to write log base E, we're just going to write ln. So in this case, when it says find the natural logarithm, the word natural refers to the letter E, which is the constant E, okay? We'll just get that E down there somewhere. There we go. So let's find the natural logarithm of a few numbers, and this is really just about, can you find the button on your calculator? So ln of 3 is going to equal what? What does ln of 3 equal? Did you find the button on your calculator? Yeah, that's good, Sean. I think I got 1.10 because you have to round it a little bit. But that's good. It's very good. So why is it 1? Because in the background, you're asking yourself, in the exponential version of this would be that e to the 1.10 is approximately 3. And that makes sense because what is e? E is equal to 2.7 something. From before, we see that e is 2.7 something. So if you wanted to raise this to a power so that your answer would be 3, then that power better be a little bit more than 1, but not 2, because if it's 2, you're going to square it, and 2.7 squared is a lot more than 3. So it's more than 6 for sure. It's more than 7. So it's way out there. So let's repeat this process for some of these other questions down here. So ln of 0.814, and you can just say ln, that's how people say it, ln of 0.814. What do you get for this one? Yes. Thank you. Now we're just going to keep on cruising along here, and I'll do a few more with you. So we'll do the next two, and then we'll move on. So we have ln of that. So this is really about familiarizing yourself again with scientific notation on your calculator. Based on your performances on tests and such, it's been very good. That is the right reason. Thank you. Based on your performances on the test, I didn't really see too many issues with scientific notation. The next one here, I'm going to try the question 2 ways. If you'll allow me the time there, I will do it 2 different ways. So the first way would be like this, just to type it the way you see it. This is the way that you should do it if you have comfort with your calculator. Just figure out how to type that on your calculator, and that's it. So I'll give you a moment to sort that out. You should get negative 2.34. So when you've got that one covered, I'll talk about an alternative way. I'll call this the fun way. Okay. Did anybody have a challenge getting this answer of negative 2.34 before I start to play a little bit here? Okay. Where did you get, Kyle? Oh, no challenge, dear friend. I apologize. It was easy peasy. Okay, so I'm going to do a little mental exercise here to kind of like show you how you could use the rules. So let's try to answer this question a different way just for the sake of practicing the rules. So here we have ln of something to the half. So I'm going to do the rule where I bring the exponent down just because I feel like it. This certainly is not the most efficient way to answer the question. Let's see if you get the answer here. Do you get like something like I'm gonna cheat here because I have the number right above us. It's 468. Something like that. Did you get that on your calculator? Like did you get negative 4.68 for the for just the logarithm of the radicand? That is the number in the root there. Can someone confirm? Cool, thank you. And then of course you get the answer on your calculator. Now why the heck would you do that? Don't do it this way. Please don't do it this way. This is just something to experiment with you. Let's put that in red and say just don't do it that way. But it's nice to know that you have it at your disposal. So I'm going to go back here and steal some text. And let's go over here. So remember that we have the phrase anti-logarithm and common before. So common anti-logarithm was base 10 and exponential. So the word natural replace the number 10 with e, and then you have the natural anti-logarithm. So in this case, if you wanted an anti-logarithm of that, that would be e to the 0.00773, which is how much? What do you get there? Correct. Thank you, Sean. Anybody else? Confirm, please. Let me know that you got something useful. Awesome. Thank you, people. Thank you very much. I like seeing. Hey, Steven, what's going on? I like seeing the different names when I know that there's it's a party, you know. So anyway, Steven's been here the whole time, but since he showed up a little late, he's got to buy everybody coffee. Not to the lesson. I mean to the conversation. So Steven, I take 2 milk, no sugar. Okay, just letting you know. Actually, you know what? I wish we were in person. I'd buy you guys all coffee in the Tim Hortons parking lot. Let's do a field trip. Anyway, where are you guys located? Like, are you guys all downtown? Or are you up in Vaughan? It's Mississauga, Oakville, Pickering, Toronto, Vaughan, Collingwood. Nice. I'm coming over for some for a bonfire. Brady, Scarves, Siobhan, Steven. Yeah, I'm Scarborough, born and raised, representing the Scarborough. I love it. Scarveria. Yeah, I don't live there anymore, but I used to live in Scarborough for most of my life. I moved there when I was 10 years old, or family, and I lived at near Port Union and Lawrence. You kind of know the area, like right at the very end of the of Lawrence Avenue. But yeah, I used to go everywhere, like Scarborough Town Center, Fairview Mall, like all of that stuff. Loved it. Johnny Burgers. Who's down for Johnny Burgers? Who knows Johnny Burgers? I'm not selling you guys Johnny Burgers. Don't worry. Okay. And then the West Enders will say Apache, of course, right? Because Apache Burgers kicks butt too. Every Saturday. Where are we? Burlington. Amir. Yeah. Yeah, I had that show on the weekend. It was absolutely barren. Nobody showed up because the weather was beautiful. Wow. Saga. Yazan. Representing the Saga. Kyle Gabriel on lockdown. No, no, no. He's not on lockdown. He's near Oakville, so he's on the border of lockdown. Just kidding, buddy. Just kidding. Uh, anyway, okay, okay. Maybe we should get back to reality. I need to make sure we cover some stuff before the break. You guys are doing really well, though. I'm very proud of you guys. Very solid group. Anyway, let's get some natural anti-logarithms. Can't even say it now. So remember, anti-logarithm is an exponential, and natural is base e. So that's e to the negative 3.18. And then we just toss that in there. And I got some decimals on this, people. What you got? 0 point something, I think. I got 2. I'm not trying to pick on anybody, but make sure you put 3 sig figs, okay? As you noticed on your midterm, I was very fair. I didn't ruin anybody. 87. Can you see it on the side here? Amir, can you see it on the side? Is it the font? Oh, okay, good. I try this dual screen thing. It doesn't go wider, unfortunately. I wish it could go wider, but it doesn't. So we're kind of stuck with what we have. This one here, 89. A lot of people had trouble with this last class. So let's sort this one out. Make sure that you can type this on your calculator. If you do have challenge typing this specific question, then what I would do is take the number in scientific notation and get that on your calculator first. What I'm saying is just type this on your calculator. Just type the exponent. Type this exponent on your calculator and write it as a decimal. Yes, Graham, thank you. Very good. That's very good, Graham. Yeah, so it's going to be roughly 1. So you should get 1. You should get 1 on your calculator. Okay. So let's do a question here where we are rearranging an equation or two. We're gonna solve some equations now, and this should be very important to the process. So I do think I need to pick up the pace a little bit at this point. So anyway, I'm gonna have to pick up the pace a little bit for the next few examples so that we're back on track. So in this first example here, which is actually more of a rearrange and solve type question, you want to solve for y here. So the thing is that you need to merge these together into a single logarithm. But there's a few things going on here. In the previous lesson, you could just kind of make both sides look like ln and then cross the lns out. But in this case, this 1 here, although it is possible to turn it into a logarithm, but it's very unnatural for people to do, especially if you're just getting used to it for the first time. In this situation, what you want to do is move everything that's not a logarithm, or move all the logarithms to one side. So take all these things here and move all the logarithms to one side. So it looks like this. And then if you can find a way to unify these and to merge them into a single logarithm, then you could combine them using the properties and find the anti-logarithm. Now I want to merge these together, but we saw this last week where if there's a number in front of the logarithm, you can't just merge these first two together or the second and the third one. So what you need to do is bring it up using the exponent rule, which we saw earlier in the class today, like that. And now we can use properties of logarithms to merge these. So remember, when you're adding two logarithms, you multiply the inputs. So if you add two logarithms together, you multiply the inputs. Like that. And if you subtract two logarithms, then you divide the inputs. And that takes you to a place where you just have one logarithm. Now that it's all one logarithm, and if you're like, can I do this every time? The answer is yes. You want to now find a way to get rid of the logarithm. So think of that word. How do I get rid of a logarithm? Anti-logarithm. So you think of the opposite. Since this is a natural logarithm, the anti-logarithm would be the base e. So that's e to the 1. And you start to get to a place where the answer is clearly in sight, because now you can cross multiply and say that x squared y equals 5e. And then you can divide both sides by x squared. And that's it, okay? If you're wondering what level of difficulty would I consider this question on a test, because of the many steps involved, I would put this as a question toward the end of a test. Just like your first test, any question that had like multi-steps, I tossed it at the end of the test. So, but the majority of the test was quick, up until like 70%, barring, of course, the linear systems question, which I promised you. Everything else was quick in the beginning of your test. So this would definitely be tossed at the end of a test. The next question, though, you could solve it in a much more fast way because it's something you could guess. So don't feel scared to guess. Like this one here, think about powers of 3. I know that 3 to the power of -3. Sorry, my finger was on the wrong place on the keyboard. 3 to the -3 equals 1 over 27, so x equals -3. So you could guess that. But let's say that you're someone that doesn't like guessing, or maybe you're just not that comfortable with exponents and mental math on that level. That's okay. Remember that when you have an exponential, you could write it the other way, which is the logarithm way. So in this case, we could say that x equals log base 3 of 1 over 27. And that's what we did in the first 10 minutes today. At some point, or in the first 20 minutes, I showed you how to type that on your calculator. We could convert this to base 10. So we can do like, or base, or ln if you want. So you would do 1 over, ln of 1 over 27 divided by ln of 3, or log. It doesn't matter which one you choose. And you would get -3. So I encourage you to at least just keep that insight there that you can definitely get the answer with logarithms. So this one is kind of like match and guess. And then this one is just full force, like just don't match and guess, just do it. So if you're wondering, like, how do I do it? It depends on the numbers. These numbers are very easy and they're small. In fact, I designed the question, so I knew that it was going to work. But if I'm writing a computer program, and I always go back to the computer program, because computer programs are dumb but reliable as long as you code them correctly. So I like to be dumb and reliable when I do this question, and that's how I would do it. I would do it like this. If I'm under pressure and the numbers are larger, or in fact maybe the numbers are not easy to determine, I would definitely hammer it out by using logarithms. However, in the remaining examples, if I see something where you could just get, you could do it without using the calculator, I'm going to venture on that route versus using the calculator. So I'm going to avoid the calculator where possible for the rest of today's class because it's too slow. This is slow here if you know the answer quickly. So moving on here, here we have another exponential question, but remember that you're trying to solve for x. So you could take the logarithm, and that's what I would do as well. So in this case, -x equals log, but in this case, it's log base e. But instead of writing log base e, you don't write that, you just write ln. And that's how you sort the question out. So x equals, okay, -x equals 2.92. And then x equals to -2.92. Now, at this second step, there was some rounding involved. So whenever I round something, I put the approximate sign. From the second to the third step, I don't put the approximate sign because I didn't round when I went from step 2 to step 3. It's just something to keep in mind. If you're not that, like, I don't know, picky as me, it's okay. As long as you get the right answer to the prescribed accuracy, in this case 3 sig figs, we're good. So yeah, I've picked up the pace a little bit in our conversation, but I think it's important that we cover up to example 96 would be good before the break. So let's see how that goes. Okay, so this next example, notice that we have 8 and we have 4. This example, you would have seen it in grade 11, just to keep you in perspective here. Notice that they're both 8 and 4 actually share a common base. They're both powers of 2. 8 is 2 to the 3, and 4 is 2 to the 2. So we could use a common base mentality here to get to the question. Now, when you look at the exponents, this here, the 2 to the 3 to the x, you multiply the exponent, so that's 2 to the 3x. Whoops. 2 to the 3x. And then on the other side, you also multiply the exponent, so 2 times x squared plus 1. So 2x squared, minus 1, I should say. And then 2 times negative 1 is negative 2. Now that the bases match, you can literally just cross them out and get an algebraic expression, which is polynomial. And from there, you're going to either factor this, it does factor, or you're going to use the quadratic formula. For the sake of time, I'm not going to show that part of the process. Based on your performance on the midterm, I do believe that you guys were very solid at this part. So x is going to equal, I'm just going to tell you the two answers. X is equal to 2 or negative a half. Wondering what I did there, I factored it. But if you don't want to factor it, use the formula, the quadratic formula, it's fine. So yeah, that's pretty gross question if you don't remember it. But if you go back to grade 11, it would have been something like the medium difficulty type question. How's everybody doing here? Are you still okay with the pace? Have I gone? Are you okay with it? So let's move on here and thank you. Let's move on here and do a couple more. This one here is one of the longer questions in terms of just using rules, but actually it's not that bad. I shouldn't say that. I answered this question two different ways in the solutions that you're going to get on Blackboard. Let me present one of the ways that I solved it, but you're not limited to just solving it these ways. So I want to get rid of, I want to move that 5 out of the way. So, because then I can use an anti-logarithm. So let's do the following. Let's move that 5 onto the other side by dividing both sides by 5. So in other words, this. What I did was I divided both sides by 5, and then you can rewrite that in exponential form. So the base is 32. The exponent is negative 3 over 5. And the output is x. Look at that. Actually, we solved it. That's it. Now, we did a bunch of these last week. We reviewed exponent laws last week, and do you remember vaguely how that goes? So remember that there's 3 operations here. So it's x equals a reciprocal. The reason that it's a reciprocal is because there's a negative exponent, like that. And then that equals the 5th root of 32, and that 5th root. And we cube it. So that's 1 over 2 cubed, or 1 over 8. So this question actually reminds me more of last week's class than this week's class. I could have actually asked you this question last week. It would have been a nice kind of capstone type question to the lesson last week. The alternative way I solved it on Blackboard is not very pleasant. This is the way that I would solve it personally. In this next example, you want to solve again by merging the logarithms into one. We saw this pattern in example number 90. So let me just say here, I'll say here similar to so you can merge them into one logarithm. So you would divide here. So it's x divided by a third. Because it's subtraction here. When you subtract, you divide the two quantities. and then you can invert and multiply. And then write it as an exponential. So 3x equals e to the 1. I took the anti-logarithm there. And then finally, the answer is x equals e over 3. So there you have it. A nice little run through of basic rules. How do you do the inverse? How did I inverse? I wrote this as exponential. So for this step here, Kyle, what I did was, remember that this is saying log base e. It's understood that it's base e. And then what you're doing is twisting it around. So the base is e, the exponent is 1, and that equals 3x. So it has to do with the fact that ln is really log base e. You're welcome. So there you have it. There you have it, a nice little review of the rules of logarithms applied to some equations, and hopefully nothing too dangerous. I would like to do one more example before the break, and then I promise you a nice friendly break. So 96. In terms of the booklet, there's the last 3 questions at the end are application with words and such. But in terms of algebra, I do think that this is the hardest question in the booklet. In terms of like the non-word problems. So how the heck do you do this one? So for this question, you'll look very carefully and you'll see that right here, you see how it says log base x of 2, but then here it says log base 2 of x. You see how it's backwards? They're backwards. They're interchanged, they're reversed. So I'm going to review with you a little property that is not in the notes but is derived. So follow me here on the side here. Log base x of 2 is equal to log 2 over log x. So far, so good. This is the part where it's going to get weird. This is equal to 1 over log x over log 2. And then that equals 1 over log base 2 of x. So there it is. In summary, what I'm trying to say on the side here once I space it out a little bit, I'm trying to say that if you want to reverse them, if I want to take that and reverse it, I can take the reciprocal. So that's how you reverse the base of a logarithm with the argument. You take the reciprocal. So that little pattern there is beneficial to this example. Because what you can do is you can rewrite it so that it looks the same for both terms. So we would have 2 log base x of 2 plus log base 2 of x equals 3. And on the next line, we could replace this one here with 1 over log base 2 of x. You see that? It's a little weird. It's a little weird, but it does something very magical. Now what I can do is apply a substitution. Because I see the same thing appearing more than once, a very predictable way to do things is to let a temporary variable equal that thing that repeats. So in this case, I could let w equal log base 2 of x. And that would lead to the following equation. 2 times 1 over w plus w equals 3. And you could multiply all terms by w and give us 2 plus w squared equals 3w, or w squared minus 3w plus 2 equals 0. That's very good because now you have an algebraic equation which is factored, and you could get the solutions for w. So on to part 2 here. So once you solve that, you get w equals 1 or w equals 2. So there's two solutions here. When you have the first solution, you can see that I'll just do it like this. Case 1, w equals 1, log base 2 of x is equal to 1, x equals 2 to the 1, which is 2. That's case 1. And case 2 would be that you have w equals 2. So if w equals 2, then you have 2 there, which the exponent becomes 2, and you get a 4. That, my friends, is enough exercises for the first hour today. Believe me, the first hour is harder than the second hour, just because quantity over quality, lots of questions. So what we're gonna do is we'll resume the class in 10 minutes, and I'll introduce to you the 3 application questions that I'd like to cover, and a couple more straightforward algebra questions. Definitely easier than this one. So that's about it. So we'll see you back at, I don't know, 9:05 is okay? All right, and a quick comment about the quiz today. I mentioned on the Blackboard announcements, and if you saw Blackboard announcements there, the quiz, for the rest of the semester, the quizzes are not going to be at 10 o'clock for you guys. They're going to be on 20 minutes after. So I'll explain right here in the chat. The quiz is open from 10:20 to 11 o'clock, and it is 20 minutes. So you could start it at 10:20, or you could start it at 10:40, the latest. Except, of course, if there's anybody that has accommodation or extra time for whatever reason. It's 7 questions, Matthew, but the first few questions are really easy. They're quick, okay? The last question is trig. The last question is trigonometry. So make sure you give yourselves at least like 5 minutes for the last question. If you handle the first 6 questions, that's fine. That's the majority of the marks right there, okay? Like I think the last questions were 3 marks or 4 marks. It's out of 17. So make sure you get the first 6 questions correct so that you're not stressed out. I need to tighten up the time on the quizzes for many reasons. One being that I can't have the quiz take. Yeah, it's based on last week's material, Jaden. And there's one trigonometry question at the end. One question involving SOHCAHTOA or sine law or cosine law. I won't say which. But it's basic. It's just like solve a triangle, something. Find some stuff on a triangle. Yeah. Okay, I'll be back at 10:05. Or sorry, at 9:05. Let's keep on going here. So we're going to try to solve another equation here that potentially could be intimidating, but once you get past the substitution, it's not so bad. We saw a question like this earlier where we had to match the bases. So I'm going to do that here as well. I noticed that 9 is equal to 3 squared. And then what you can do is you could reverse the exponents because they're being multiplied anyway. So I'll put the x inside and the 2 outside. And then do a substitution. So you end up with a quadratic equation. And we've solved a bunch of these before. And we did one today earlier in the previous example, at least. So we get here that w equals 4, or w equals -3. So each of those situations will provide one possible solution. Let's take a look at case 1. If w equals 4, we get 3 to the x equals 4. That one is not nice. That's not something that you could guess, because 4 is not a power of 3, that is an integer. So let's use logarithms. So that's log base 3 of 4. And if you don't have that button on your calculator, you could type it as log 4 over log 3, which eventually gives us an answer of approximately 1.26. The second case is not so promising. With w equal to -3, you have 3 to the x equals -3. Now, although the right-hand side looks like 3, it's -3, so it's not actually a power of 3. And this is an impossible situation. So there's only one answer to the question, which is 1.26. And that's it. Let's move on to the next question. The next question is a bit more historical than anything. You may notice in some textbooks or references that you encounter, maybe they're older references. It was very common for mathematicians to use the exp operator. And the reason is because it was difficult to write things as powers of powers on word processors, but that's not the only reason. It's also very nice to read. This question is saying the following. When you see exp, it's like it's saying e to the. So that's what the actual question is asking. Or in other words, exp is the inverse of ln. exp is the inverse of ln. So you could write a question like that. Now, ln of 9.14 is something that you could type on your calculator. And that's roughly 2.2127. And then you could take the square root of that, but remember that plus and minus because it's x squared. So the answer would be 1.49. So that concludes the application questions. The mechanical type solving equations and practicing your rules of logarithms. The remaining questions that I'd like to cover with you are application in nature. So word problems, practical things, real life things. We're going to start off with example 100, and then we'll do 101, and then we'll come back to 99, because 99 is by far the longest question in the chapter. So if you look on the next page here, we're going to skip this question. As you can see, I've given an entire page to solve it, and it is the longest example, probably one of the longest examples in the course. So we're going to come back to that one. One of the reasons that I was teaching you logarithms in this unit is because finance is a very important aspect of construction and construction management. So it's very important that you know how to use compound interest. Let's talk about the compound interest formula. So recall that the compound interest formula, and I'll use the notation that's in this question, but you can change the letters around as you need to. So in this question, the exponent is t. So just to refresh your memory, future value, present value, interest rate, and time. So those are the quantities that you need to know for compound interest. So in this specific question, so for answering part A here, for this question, we know that today we're going to borrow 25,000. So A equals 25,000. And the interest rate is 3.7%, which we immediately convert to a decimal. And that allows us to create the formula for the value. So value will equal 25,000, 1.037 to the t. So that's part A of the question, writing down a formula for the value. Last week in class, I remember doing a question just like this with you, and I deliberately said that we would revisit a question like this today. Now that you know logarithms, it will make solving the last part of this question a lot easier. And what we see here is that the part A and part B are something that doesn't matter if you know logarithms. So let's take a look at part B and just solve for whatever it's asking. And who cares if you know logarithms? And then the third part, it will be valuable. So in part B, it says find how much the debt is going to be after 10 years. So what do you do? How do you do part B? What do we do? Yeah, plug in 10 for what? For t, thank you. So set t equal to 10. It's 10 years, but I'm not going to worry about the units right now. That's fine. So if we go back here and plug in 10, how much do you get? Yes. Very good, Stephen. I can't even steal your text. Can I? Oh, I can. This is so satisfying. I just stole Stephen's text from the chat. Look at that. I'm a thief. You guys are doing all the work and I'm just copying and pasting here. I love it. Okay, anyway, you get 35,000 and change. Not bad. It's part C that I'm most interested in discussing with you, because in this part, we're trying to solve for the time. And last week, we talked about solving using guessing. So for part C, last class, we guessed. table of values. So let's try to use logarithms here. So let's take this equation here. And plug in 40,000 for the value. So we're going to simplify it a little bit first before we actually go and evaluate a logarithm. Let's divide both sides by 25,000. So hopefully you're okay still with that. This is a big milestone in the question. So what you want to do here now is figure out how to get t with logarithms. So what do I write here? How do I write t as a logarithm? What's the base? And then the answer is 1.6. Perfect. Thank you, Yuzen. And then we're going to have approximately 17 years. You have to round up, okay? Even if you are compelled to round it down, don't. Round it up. Oh, it's 13, sorry. I think it's 13. I redid that on my calculator. So it's going to take 13 years to achieve it, because if you rounded it to 12, let's say it was closer to 12 than 13, you're not going to reach it at 12 years. The debt it's like crossing the finish line. You don't, like if you're in a race, you don't round to the nearest meter. You have to cross the finish line. So anyway, there's example 100. It's quite comprehensive, and it is a blueprint for what my expectation is from you regarding compound interest. I haven't created your final test, and I know that's a ways away. It's over a month away, but I'm going to look for questions involving compound interest. So do be aware that there will be, most likely, I'm almost say 100%, but I'll say 99%. There will be compound interest question or two on your final test. So just be aware that that'll be not a possibility, a likelihood, like almost a certainty, I should say. So now that you've understood question 100, hopefully better, as it is very similar to last week, what we're going to do is just another one of these part C's. Why did you put 1 plus the interest rate? Okay, so it's always 1 plus the interest rate. So the idea there is that the 1, like when money grows, you're adding a percentage back. So if I just multiplied the current value by 0.037 times 25,000, let's say for the first year, you're going to get a number, whatever it is, 6, 7,000, whatever that number is. But then you need to add it back to the 25,000. So the 1 is like saying I have to add it back to the 25,000. So if you want, you can say 1 plus is what you have plus the extra stuff you're getting, which is the I. It's a good question. Very good question. Alrighty, you're welcome. Thank you, Yazan. That was a good question. So let's do question 101 here. Now it's the same thing. So I'm just gonna I'll steal the form. Actually, I'll take this whole thing here. and I'll recycle it for this question. How do I input this on my calculator? Matthew, are you talking about the last step? Oh yeah, so remember that when you have something like that, then you're going to type in a fraction. You're going to go log of 1.6 over log of. Thank you for asking. Try that out. Let me know. Did it work? You're welcome. Yeah, so that's how you do those weird ones. Some people have a calculator where you can do it in one step and you don't need to know this property at all. But my calculator does not have it, and it's better if you know it both ways. Plus, if you're just doing it on the phone, let's say that you're somewhere in a meeting and you're trying to do something like this on an iPhone or an Android phone, most likely you're not going to have that special button that looks exactly like this. Sorry, that looks like, what did I just do there? I just broke it. That was so weird. Most likely, you're not going to have a special button that looks like that. You're going to have to figure out an alternative, which is the basic rule. So question 101 is kind of your opportunity to bring it all together. So let's work through this one carefully together and see how it goes. So the question's asking, what is the future value? Oh, sorry, what is the time? It says how long. So when you see the words how long, how long means time. So let's sort that out here. So the future value is 250,000. Present value is 100,000. Interest rate is 6.43%, which I'll immediately write as 6% and a little bit extra. Let's plug everything into this equation. And now, what do we do next? Yep. And then we could either guess the answer or we could use logarithms here. So I'll use logarithms. That'd be log base 1.0643 of 2.5. And that looks like the previous one that you were asking about, Matthew. So you can try this one now. So that's log of 2.5 over log of 1.0643. Remember to round up. And that, my friends, is enough of the compound interest. So we did many examples, and I hope that you've built some confidence with compound interest. Of course, for the most part, this is or should be a review of stuff that you've seen back, hopefully in grade 11, at least in the Ontario curriculum. But even if not, or even back then, let's say that you didn't really follow or understand it well, now you have it. Now you have it available to you. So that leaves us with a pretty generous amount of time for the last example, and it goes back to the St. Louis Arch. Do you remember that gateway arch question that we talked about? So For those that are kind of, thank you, Mason. So for those that don't remember the gateway arch, let me just look at a picture. The restaurant. Still waiting for that, eh? You guys are being very good, very, very well behaved. Well, just because you guys are so nice, I'm going to give you a different picture of it. So who remembers how tall this thing was? No, but it's close. Closer. This is like hot and cold. Closer. No, that's cold. You're cold, Yazan. Warmer, warmer, warmer. I mean, Austin was on fire. There it is. Graham. Winner. Winner, winner. Yeah, it's 192 meters, I believe. And what you're going to discover now is we're going to calculate the width of it. We're going to calculate how wide it is. God bless Google. So let's go over here and let's assign an axis to it. You know, I'm feeling pink today. Let's do a little pink. So, whoops. There's the origin. There's X. And there's Y. I apologize for the slow drawing here. It's the stylus, it's not me. I think a lot faster than that, don't worry. Anyway, if you notice on the diagram, we're going to actually solve for two x-intercepts. There's one over here, and there's one over here. We're going to call these, I haven't really specified which is which, so I'll call this x1 and I'll call this x2. And the question's asking, find the width of the arch. So the width of the arch, I won't use actually I shouldn't use letter W. I have it reserved for something else. I'm going to say that the width is x1 minus x2. So this is what the question's asking for, is what is the width of the arch? So we have enough information that we can proceed. This question really is going to challenge everybody in the class. This is definitely a scary question. So let's see if we can use the skills that I've kind of provided you with to make sense of this question and solve it. So the first thing that we're going to do is we're going to try to make that these e's here, see these exponentials, they kind of look the same. They kind of look the same, but this is negative. We're going to try to make them look the same. Now, if we're going to find x-intercepts, we should set y equal to 0. But it's not y in this case, it's h of x. But y is h of x. So if we do that, we get 0 equals, and I just have to copy the equation, so just bear with me here. Now, what I'm going to do is I'm going to try to make them look the same. So if I can somehow alleviate, or get rid of, I should say, the negative sign here, we know how to do that. Negative means flip. That's based on last week's class. And there's the hint. There is the key to this question. You see, we have the same thing appearing twice. Didn't we see this a couple times at least already today, where I saw the same thing, although complicated, I saw the same thing repeating, and then I let W equal it, or whatever letter you like? Well, I'm going to do the same thing here. I'm going to let W equal, whoops, where did W go? I'm going to let W equal that. Let's see what the equation turns into once you do that step. You get W, and then 1 over W. That looks very promising. That looks very promising. So once we solve for W, we will have to go back and get X. But for starters, that's pretty good. What you want to do now is, like, you could get rid of one of the decimals here by dividing everybody by 19.5 if you like. Let's do that. Let's divide everybody by 19.5. I mean, this step is really not necessary, but I just like to have less decimals floating around. So over here, this will become 11.8410. And yeah, just allow the extra decimals there because it's beneficial. Since we're dealing with exponentials, with exponentials, it's a good idea to carry more digits because they rapidly change. Get rid of that negative sign. We also saw this little thing here appear in a previous question where we had 1 over W, and a couple times. And I mentioned to you that, see, the questions that I was showing you earlier were kind of like building blocks toward this. So that's why I was showing you all those weird things earlier with the 1 over W and the temporary variables. So here I'm going to multiply everybody by W. So if we do that, we get, I'm not sure why it's not centered. Let's center it up here. There we go. This step is optional, but I am going to multiply everybody by -1. And that, my friends, leads us into a very good place in terms of this question. See, now we have a quadratic equation, and we can solve for W just like you would solve for something with X. So let's on to part 2 of this question. There's no parts to it, but in terms of the algebra, we can solve the quadratic now. So A is 1, B is -11.8410, C is 1. Then you can use the quadratic equation here. I'm not going to show these steps if you don't mind. I think that this is something that you should be better with now, especially after the midterm. You will get 2 answers, which are 2.4644. Sorry, that's wrong. My apologies. I did an extra step on my calculator. So you should get those answers. Like that. And of course, this is not something that you do in 10 seconds. So there is a lot of work involved there. And if you have a program on your calculator that does that for you, all power to you, that's fine. So, but where does that leave us though? Once we solve for W, what would we do next? What are your thoughts on that? Yeah, change W back. Thank you, Stephen. So I feel like coloring it a little bit. Let's make this blue. I like blue there. And then we can make this, this is the red phase. Kind of like the dark side. Star Wars, part 2. No, sorry, part 5. Empire Strikes Back. And now we're going to do Return of the Jedi. We're going to go to the world of X again. So there's two cases. Let's talk about the two cases. Sorry, just saved in the file there. So case 1, W equals 11.7559, which means that e to the, let me just see here, x over 38.9 equals 11.7559. We don't want the e there, so we could write this the other way, which is the logarithmic way, which is base e. So we get that x over 38.9 equals ln. It's log base e. Just to be clear, it's log base e, excuse me, of 11.7559. But we don't write log e, we write ln. Because that's what log base e is defined as. So that's something that you could type on your calculator. So I'll do it like this. I'll do x equals 38.9 ln of 11.7559. Can someone do that on their calculator? What do you get? 2 decimal places if possible. Yeah, I got 95. That looks good. I got 95.87, but Matthew and I are on the same page. It's good. 95.87. Now, nothing wrong with Matthew's answer. It's within 1 digit. But when I did these ones, I did it on the computer, and I kept more digits. It's all good, Stephen. You've been on a very good streak anyway. So anyway, you can put, just for the argument's sake here, you could just put 95.9 on. Then there's no issue. Yeah, I got 863. Okay, yeah. So I'm gonna just go with 95.9 to minimize the debate there. Thank you, Mason. And that's okay because the thing is that exponentials, they do have very large swings, meaning like a very small change in the number on an exponential or a logarithm can do a profound difference or a profound change in the output. Exponentials are very, very wild, as you can imagine, because they start off shallow and then they just go crazy and they fly up, right? Or vice versa. So anyway, that's the first answer. That's case 1. So I'm going to just copy and paste this. Let me just change the font a little bit. We're almost out of the woods, people, here. So that's case 1. Let's do case 2 as well. So case 2 would be that this is equal to 0.08506. I'm just going to copy and paste that throughout the answer here. And I'll rely on you to type this on your calculator. So whoever's done it already, I'm sure someone's tried that already. Let's hook me up with a number here, people. Negative. And you know what? Many of you may have seen that it would be the same number. Let's go back to that picture. Let's go back to that picture. See how it's symmetric? If you know one of the answers, all you need is one of the answers. So me doing case 2 on the calculator, thank you by the way, Graham. Me going on the calculator and doing this is actually more of a check. If you're confident that you did the first one well, then you don't need to do the second one because of the symmetry. But nothing wrong with doing the second one and then in hindsight discovering, oh my goodness, of course it's the same number but the opposite sign because it's a reflection in the y-axis. Anyway, all that aside, we have what we need. On the diagram, the positive answer is x1 and the negative answer is x2. So I'm going to just go back here for a second to make it correlate better to the figure. I'm going to call the first solution W1 Whoops. And the second solution, W2. And if you'll bear with me for a second, I don't know why it's making the case size larger. That's weird. Sometimes, see what it's doing there? It made it uppercase. I didn't even hit any caps lock buttons. It's weird. It's not even me doing that. It's so weird. Anyway. If you can't beat them, join them. There we go. So there's your two solutions, W1 and W2. What color are you feeling, people? What do you want? You want like a fuchsia? You want a fuchsia? You want a gold? What would you like here? Green. Sean, I was thinking green too. That's crazy. That's right, Star Wars theme. I knew you were going to say that. That's Luke's lightsaber. We got the green lightsaber now. And the blue one's Obi-Wan. Oh my god. Life is complete. We figured everything out. We've solved the riddle of life. Anyway, let's finish the question now. So the width of the arch, the width of the arch is equal to, thank you. That was awesome, Disikrat. I'm with you there, my friend. Okay, so we're going to do x1 minus x2. Anyway, if you subtract those two, you're going to double it, and you're going to get what? 191.8. Can someone confirm 191.8? S'il vous plaît. Merci beaucoup. Merci beaucoup.